We've seen now how to solve the directly integrable equations. But now we're going to have a look at solving linear differential equations with constant coefficients. We'll start off with the homogeneous type, where the right-hand side is 0, and in this lesson, let's have a look at the general solution. So this is the kind of equation we're going to try to solve here. Variable x, function y, one constant a times the second derivative, plus another constant b times the first derivative, plus a constant c times our function is equal to 0. That's the kind of equation that we're going to have a look at. And we start off by replacing this equation, this differential equation, with an algebraic equation, a quadratic. A times m squared plus b times m plus c is equal to 0. So the coefficient of the second derivative becomes the coefficient of the second power. The coefficient of the first derivative becomes the coefficient of the first power. The coefficient of the function becomes the coefficient of the constant. We call this the auxiliary equation. And actually what we're doing here, if we replace y with an exponential, we end up with the equation here. And in particular, the reason that we're looking for an exponential is that because the function, the derivative, and the second derivative add together to give 0, we're looking for the kind of function that is of the same form as its derivative and its second derivative. And certainly the exponential satisfies that. So we form and then we solve this quadratic equation that we call the auxiliary equation. And then depending on what we get out of this equation, we have slightly different forms that we're going to use. So this quadratic equation will have two roots. If we're talking about two roots which are real and distinct, well, let's call them m1 and m2. In that case, the solution to our differential equation is one constant p times the exponential of m1 times x plus another constant q times the exponential of m2 times x. We'll have constants p and q. Now, of course, you can call your constants whatever it is that you like. Letters near the beginning of the alphabet or letters around p onwards are often used. Obviously, once you get past about t or so, you're generally getting onto variables there. The other thing to bear in mind, it might not be y as a function of x, but you would adapt your notation accordingly. If your two roots are real and distinct, we have the sum of the two exponentials. But we might have a situation where the two roots of our auxiliary equation are real and equal. So we'll call them m, and in that case, the solution to our differential equation will be one constant multiplied by x plus another constant, and the whole thing multiplied by the exponential of m times x. This gives a solution in that particular case. Again, for constants p and q. Remember, it's a second order differential equation. We would expect there to be two constants there. And the third case is if our roots are complex. Now, because our a, b, and c, we're assuming that we're starting off with real coefficients. So if we're going to get complex roots, they will form a complex conjugate pair. Lambda plus or minus I, the imaginary number, times mu. So we've got a real part, lambda, an imaginary part, mu. And in that case, we can write the general solution as the exponential of lambda x multiplied by one constant p times the cos of mu times x plus another constant q times the sine of mu times x. Again, for constants p and q. So that's the three cases. Let's have a look at a couple of examples. The first example here, twice the second derivative minus 9 times the first derivative minus 5 times the function is equal to 0. And we notice we have y as a function of t. So let's go ahead and try to solve this equation. So the differential equation here, 2 times d squared y by dt squared minus 9 times dy by dt minus 5 times y is equal to 0. That's the differential equation that we're solving here. And, well, we could write down the auxiliary equation. And that would be 2 times m squared minus 9 times m minus 5 is equal to 0. That's the auxiliary equation. Now we can go ahead, factorize it, solve it, but let's just justify this auxiliary equation. If we say we are looking for solutions y is equal to the exponential of m times t. Well, if that's the case, dy by dt is equal to m e to the m times t, and d squared y by dt squared will be m squared e to the m times t. So putting all this into our original equation, we'll get 2 times m squared e to the m times t minus 9 times m e to the mt minus 5 times e to the mt, if we want that to equal 0. Well, we can factorize, we can take out an e to the m times t, and we're left with 2m squared minus 9m minus 5. If that equals 0, well, the exponential can't equal 0, so we do indeed have the auxiliary equation 2m squared minus 9m minus 5 is equal to 0. Here, we simply wrote it down on the basis of the coefficients of our original equation, and generally that's what we will do, but we did justify it in this case. So here is our auxiliary equation. It factorizes 2m, and in m we'll have a 1 and a 5, minus 10m plus m gives us our minus 9m. So if this product is 0, we'll have that m is equal to minus a half, or m is equal to 5. We have 2 real and distinct solutions here. So now, on the basis of knowing those values of m, we can write down our general solution, and this general solution, YGS for general solution, will be 1 constant times e to the minus a half times t plus another constant q times e to the 5t. this is the general solution to the differential equation here. It involves two constants here. I've called them P and Q, but you could give them other names, or indeed you could give them P and Q the other way around, or one of P and Q and one other thing, but generally there's a few sensible combinations that keep coming up. So here we have the general solution. Second example, we have z as a function of x. The second derivative plus 6 times the first derivative plus 58 times the function is equal to 0. So again, let's go ahead and solve. So our differential equation, d squared z by dx squared plus 6 dz by dx plus 58z is equal to 0. Second order, linear, constant coefficients, homogeneous, z as a function of x. Let's write down our auxiliary equation. We have m squared, 1m squared, plus 6 times m, plus 58 is equal to 0. Now we could use the quadratic formula, or we could complete the square. Right, m squared plus 6m plus 9 plus another 49 is equal to 0. M squared plus 6m plus 9, well, that is m plus 3 all squared. And if we subtract 49 from both sides, so then if we look for m plus 3, the square root of minus 49, well, it gives us plus or minus 7 times I. So our m is going to be minus 3 plus or minus 7i. We have a complex conjugate pair. We could say lambda plus or minus I times mu, with lambda is equal to minus 3, mu is equal to 7. So now we can write the general solution. Z, gs for general solution. Remember, it's z as a function of x. So we'll have e to the minus 3x, and then we'll have p times the cos of 7x plus q times the sine of 7x. So this is our general solution. We could verify it by working out the derivative and the second derivative, and we'll see that when we add them together in this combination, we will get 0.